So it's about an alternative to convolutional neural nets. I should say the version I'm going to talk about doesn't really work very well. Since then, Sarah Sabor at Google has got it working quite a lot better. But I'll talk about the old version because that's what I haven't had the slides for. So most people who do neural nets now, sort of 10,000 graduate students in China who are doing neural nets, believe that the way a neural net works is that you have layers of ReLUs, maybe you have an LSTM, and that's how neural nets work. What they don't realize is we just made that up. It doesn't have much to do with the brain. I mean, it's inspired by the brain, but because we just made it up, it's perfectly possible there's very different architectures that work better. And I'll give you a little lesson in history. For 30 years, people tried making neural networks work with a sigmoid unit. Now, some brave people said, let's not use a sigmoid unit, like Yann LeCun said, let's not use a sigmoid unit, let's shift everything down a bit and multiply by a factor of 2 and use a tan-H unit. And there was a big debate about whether you should use a sigmoid or a tan-H, because tan-H is better if you've got ill-conditioned problems and things. And that was pretty much it for the exploration of the kind of nonlinearity you should use for about 30 years. And it turns out that if you use the max of the input and 0, that actually works quite a lot better. It's easier to backpropagate through many layers. There's all sorts of reasons why generally that works better. But people weren't looking, right? They just weren't looking. So if it took them 30 years to discover that a rectified linear unit, which people in neuroscience were recommending ages ago, I was actually using them about 2004 because a guy called Hugh Wilson at York said that's much more like a neuron than this sigmoid units, because neurons almost never saturate in their normal regime. So you shouldn't be using sigmoid units. So I tried to work, and they sort of worked, but I never did the experiments to show that they actually work better. And then later on we did. So what I want you to understand is that our field is in a situation where suddenly a particular recipe is working extremely well. It's actually working well enough that it's useful, and it beats conventional computer vision techniques. It's pretty much the recipe Yann LeCun has been advocating for many years, except with rectified linear units. And there's no reason for believing that there aren't very different things that are much better. Okay. So here's a very different thing that isn't much better. So I solved half the problem. Maybe in the end it will be. And if you go right back to the beginning of neural nets, at the beginning of neural nets, I'm going to do a lot of ad-libbing in this lecture because I've got a license to. At the beginning of neural nets, people said, well, you can't do XOR. And other people said, well, it's true, you can't do XOR with one of the kind of units we're using, which takes a sum and puts it through a logistic or a hard threshold. That is, you can't make 1, 0 and 0, 1 as inputs, give a 1, and 0, 0 and 1, 1, give a 0. Just in case you are too young to remember XOR. Now that's very unfortunate that they chose XOR. They could have chosen something that's logically equivalent to that, which is the function same. You can't make one of these units give a 1 if it gets 2 1s as input or 2 0s as input, and give a 0 if it gets 1 0. It's just the same function with a negation in. Okay? So you can't make one of our standard units do same. So what's the standard solution to it? The solution to it is to put in a hidden layer and basically subdivide the cases into there's a sort of 1 1 case, and you have something recognize that, and there's a 0 0 case, and you have something else recognize that, and then if it's either of those, it's the same. So that's one way to handle what we might now call the same problem. But there's a completely different way to handle the same problem, which is to give yourself a neuron that can do same. Now, you might ask if there's any neural inspiration for this. Well, there is actually a neural inspiration for it, although it's not very relevant to this talk, which is neurons send spikes. And we know that in some places, like, for example, dealing with the tiny delay between the two ears that tells me the difference between that direction and that direction, that's a delay of about probably this much for sound. And this much for sound is a millisecond, so it's a delay of like much less than a millisecond, the difference between there and there. And we can deal with that, and we do it by sending spikes either way. I'm aware that Doug Tweed is here and probably knows how we actually do it. But we send spikes either way, and we have things arranged to look for the coincidence, and then you can tell. So you do it by the coincidence of spikes. So we do have coincidence detectors, and we suspect they're used in other places too. So it's not totally neurally uninspired, but for now, forget the brain. We could have a different kind of unit that can do same. And that's got very different properties from the neurons we have at present. So the neurons we have at present can do the following. They can take an input vector, and they can take a weight vector, and they can tell you how well they correlate. They take the scalar product, but they could normalize if they like. They can tell you, does this input vector and this weight vector correlate? What they can't do, conveniently, is take two input vectors and tell you, do those correlate? Two activity vectors. They measure correlations between weight vectors and activity vectors. And if you want correlations between activity vectors, you could have a whole bunch of different units that measure, do they correlate with this weight vector and this weight vector and this vector, and does this one do it? And you can imagine making a circuit out of what I call normal neurons. But you might just say, why don't we have neurons that can detect whether two high-dimensional vectors are the same? And maybe if we can do that, there's certain computations that will get a whole lot easier that were difficult, and certain computations obviously will be more difficult. But it might sort of change the way you do business if you had, as a sort of basic unit, something that can detect coincidence. Okay, so that's one of the motivations here. Another motivation is, why should we stick with neurons that do scalar nonlinearities? So at present, our neurons, they apply a linear filter, they get one number, and then there's debate about what scalar nonlinearity to apply. There's one place where we use neurons that use vector nonlinearities, which is a softmax. In a softmax, the output of every unit depends on all of the inputs. So that's a vector nonlinearity. So intrinsically, it takes a vector and gives you out a vector, and everything depends on everything else. It's not a bunch of scalar nonlinearities. You can quibble, but basically not. But what I want to say is maybe let's think about the space of vector nonlinearities. It took us 30 years to go from this guy to this guy, and I think you can imagine there's a lot more vector nonlinearities than there are scalar nonlinearities, but we should be exploring that space in case there's good ones, and we better have some motivation, we better have some insight into what we're after. And I think being able to deal directly with covariance in activities is what we're after. If you take an image and you measure the covariance structure, and then you change all the intensities, but keep the same covariance structure, and you show it to someone, they'll say, oh, that's just a different rendering of the same thing. If you keep the intensities pretty much the same, change them a bit, but change the covariance structure, they'll say that's something quite different. It's the covariance structure that really matters in an image. And so why not have neurons that pick up on covariance structure directly? Actually, I think my ad-libbing is much more convincing than the slides, because the slides, you know, you get to see hard facts you can disagree with. So the idea of a capsule is a vector thing. It's got a vector activity, and capsules in one layer send information to capsules in the next layer, and the capsule in the next layer gets active if it sees a bunch of incoming vectors that agree. If you're a computer vision person, think Huff transform. Now, of course, a capsule in the next layer doesn't see just the output of the capsule in the layer, but it sees the output multiplied by a weight matrix. And so this capsule sees the output of this guy multiplied by a weight matrix, and the output of this guy multiplied by a weight matrix. And if those two products of an activity vector and a weight matrix agree, and maybe it sees many more, if it gets good agreement, even if there's some outliers, it will say, hey, I found something. And of course, a high-dimensional coincidence, if you get, say, 6-dimensional things to agree, even if each dimension only agrees to within 10%, the chance of a 6-dimensional thing agreeing is like 1 in a million. I mean, if it's sort of a tenth of the normal disparity on each dimension, then it's a millionth of the disparity of two random things. So a high-dimensional agreement is a really, really significant thing. and is a much better filter than what we do at present, which is you apply some weights and see if you get above the threshold. Obviously, we know that if you stack that up and you train it by stochastic gradient descent, it can do anything, and actually it can do amazing things. But if you go back to basics, it's not in its nature to sort of automatically be looking at covariances between vectors. And I want units where that's part of their nature. Okay. So the idea of a capsule is it'll have a vector, and what that vector will do is it'll represent the different properties of a thing, of an entity. Now the entity might be a little fragment, or it might be something much bigger. And if we weren't doing vision, it might be something else altogether. But the other aspect of capsules is we're going to try inside the net to get entities. If you take a typical neural net, it's not sort of committed to entities. It has a big layer of ReLUs, and then another big layer of ReLUs. There's not more structure than that. There might be local connectivity and convolution and so on, but it's not committed to finding multidimensional entities. Whereas if you look at how people deal with the world, they deal with the world in terms of objects that have properties. So if we go back to the time I was reading the literature, Hebb published a book in 1949 called The Organization of Behavior, where he said something very interesting. Everybody here knows about Hebb because he talked about the coincidence of postsynaptic and presynaptic activity being something to do with how neurons change. He didn't say it was a product. He said both of them were involved in how synapse changes. But he said something else, which people ignore, which is we're never going to understand anything about vision until we understand why vision, why when you do vision, you get objects, why it always happens in terms of objects. And we don't really understand that. And capsules is also addressing that concern. It's saying we're going to understand the world in terms of entities, and these entities are going to have properties. And what a capsule is going to do is it's going to make a fundamental commitment. So if you go back to a long time ago in NIPS, there was something that in the NIPS community was called the connectionist binding problem. Some people thought that meant there were too many papers submitted to NIPS to be able to put in one volume without the binding breaking. But that wasn't the connectionist binding problem. The connectionist binding problem was, if you've got, say, a blue circle and a red square, and you try and represent them in terms of one-dimensional things like blueness and shape, you'll activate blue and red, and you'll activate square and circle. And the connectionist binding problem is here's blue and red, here's square and circle, and they're different coordinates. And we don't know whether there's something here and here, or something here and here. You don't know what goes with what. And so long as you have multiple things, you can't represent them by just representing their coordinates. You have to sort of put brackets around them, if you see what I mean, to hold coordinates together. So the idea of a capsule, there's another idea in a capsule that works for vision nicely, which is that we're going to assume that in one region of an image, you only have one thing of a particular type. Obviously, when we're dealing with things like edges, that means we better use pretty small regions. If we have something that detects an edge, you better say in one tiny region of the image, there's only one edge, and I just have to decide what orientation it's in and whether it's there or not. This will work when you're dealing with vision of opaque objects, because in any direction, you only see one thing. When you look through windows, that's violated, but let's not worry about that. So if you want to use the activations of a bunch of different units to represent different properties of the same thing, which we do in a capsule, you'd better believe there's never more than one of those things in your receptive field. In fact, you better make that's a sort of fundamental commitment that you make that enables you to use simultaneity to solve binding. If I'm a capsule and I've got a bunch of units, and several of them are active at once, then just the fact that they're active together means they apply to the same thing, and so I've solved the binding problem. I sort of cheated. We actually solve the binding problem at a higher level by going sequential. If you go sequential, that is only do one thing at a time, then you can bind together arbitrary things just by simultaneity. I want to do that at a low level too, in each of these capsules. Okay, so there's a big commitment here which says you can't have two of the same thing in the same place, in the same receptive field. Now, you might think that's a very, very strong commitment and not really a good idea. There's lots of psychological evidence that I take to corroborate that position. It's certainly compatible with that position, which is called crowding. When you put in the same receptive field several different features of the same kind, it gets much, much harder to see things. There's a psychologist called Dennis Pelly at New York who's done a lot of research on this. And it turns out the difficulty of seeing things isn't to do with how big they are. You can make them very small and still see them very clearly. It's to do with whether there's similar features in their immediate surroundings. If you have that, you can't see them very well. It's hard to read. You've probably all had this experience. If you take a page where you've got nice font, if you enlarge the letters but keep the spacing the same, it gets much harder to read. And that's because you get crowding. And if you've got something like that and you shrink the letters, it gets easier to read. That's kind of amazing. Okay, so that's the evidence that really we may have this commitment to only one thing of a kind in a position. And low down in your visual system, it's simple things. As you go higher up, it's complex things. So when I get up to face capsules, I'm going to make the commitment that, obviously I fixate somewhere, and in any region, I might have multiple things that can detect faces, but each one of those capsules can only see one face. Okay. Associated with each of these, Associated with each of these capsules, I'm also going to have something that says whether it's active or not. So I'll have a logistic unit, because logistic units are good for probabilities, that says, is this thing present? So let's suppose I'm a capsule and I'm getting votes. Typically we think of these as high dimensional votes, but I'll just use 2 dimensions because it's easy to draw. So all those things are votes. If I see a pattern of votes where there's all these kind of stray votes, and then there's a number, not necessarily a big number, that all agree tightly, that's evidence that my object is there, my entity is present. Because there's a whole bunch of lower level entities all saying, I think the kind of entity I might be part of is present, and these are its coordinates, these are its properties. And if the properties agree, if you think about sort of filtering terrorist chatter, if you see some message, you intercept some message and it says September, and you intercept another message and it says New York, and you intercept another message and it says 2001. And you might see lots of messages that say September, and lots of messages that say 2001, and lots of messages that say New York. But suppose you get a small number of messages and each of them says September the 11th, New York. That is, it's just a coincidence of a place and a time. But if that same coincidence keeps cropping up, then that's much stronger evidence than if just the individual terms crop up. Okay. So you can think of that as you're looking at the covariance of things in messages and seeing the same covariance pattern, and that's really good evidence as opposed to the individual things. So now I'm going to trash one of my favorite researchers, Jan. I'm a bit late, actually. The field has already trashed this. When I wrote this talk, everybody was doing max pooling. Now people are quite happy not to do max pooling. You can just, you could stay, if you liked, with the pixel grid and go all the way up with the pixel grid, and these ConvNets would still work just fine. So really, when Jan was doing ConvNets, he thought the max pooling was a really crucial point of the ConvNet, and that's how you're getting invariances, by ignoring exactly where a feature occurred. I don't think that's the most interesting aspect of ConvNets, and I don't think that's the right way to get invariances. So when I see a face, and the face moves, or changes orientation, I'm aware of the change of orientation. When I see a face, I see not just that it's a face, but I see all the relationship of the face to my retina. That is, the things to do with viewpoint. I'm aware of all those. So it's not that my representation of face, my full representation of the face, is independent of the viewpoint. Obviously, the bit that says the face capsule got excited, that bit will stay excited even as they change the viewpoint. So that's an invariant bit. But the representation of the face includes all these properties, and these properties all change when the face changes. So what we really want is, at least in capsules, is we want equivariance rather than invariance. We want it that when the properties of the object change, the properties of the representation change in the same way. And convnets do that for you. Do I have a picture? No, I don't have a picture of that. So, an important property of convnets was pooling, and capsules are designed to be an alternative to pooling. I'll race through that bit. If you ask how one of these convnets sees things after these layers of pooling, it's lost information about the pose. At least it's lost explicit information about the pose of the object. Obviously, the information is in there implicitly in the relative activations of all sorts of filters. And one particular thing a convnet can't do is it can't have very different percepts of the same input. So here's a bit of psychology now. If yeah, this talk's going to be very rambling. I have a wonderful excuse for a rambling talk, and eventually the clock will stop. We get to 1 o'clock and I'll stop. If you take a square and you rotate it 45 degrees, so here's our square rotated 45 degrees, you can perceive that as a square rotated 45 degrees, or you can perceive it as an upright diamond. And those are utterly different percepts. That is, if I show it to you, and then take it away and ask you questions, the questions you can answer are completely different depending on which way you perceived it. So if you perceived it as a tilted square, and I ask you which was higher up in the image, this corner or this corner, you'll have no idea. If you perceived it as an upright diamond, you'll be exquisitely accurate to which corner was higher. If I show you an upright diamond, and the angles aren't quite right angles, and you see it as an upright diamond, you'll be completely insensitive to whether the angles are right angles. You just won't know. If you see it as a tilted square and it's slightly off a right angle, you'll be exquisitely sensitive. Okay, so you know different things about the object depending on the frame you impose. In other words, our knowledge of objects is all relative to the frame we impose. I've got lots of demonstrations of that, and I can't resist giving you my favorite demonstration, which some of you will have seen already. But hopefully most of you are young enough not to see. If I take a cube, a wireframe cube on the tabletop, how many people know this demo? Not very many, great. I take a wireframe cube on the tabletop, and it's a big wireframe cube. It's made of black, matte black rods, okay? And the rods are about this thick. So here it is, big cube, and you can imagine that. And if I ask you where the corners are, you can say they're here, here, and so on. Now, from your point of view, I take the top, front, right-hand corner, and the bottom back left-hand corner, okay? Those are two corners of the cube. And what I'm going to do is I'm going to rotate the cube so that this corner, a cube, right? What could be simpler than a cube? I rotate it so that this corner is vertically above this corner. So here we go. Okay? And now here's what I want you to do. I want you to take the fingertip of your left hand and put it at a fixed position in space, and that represents this corner. Off you go. Left hand. Okay, and now I'm going to take your right hand and put it, and above this corner, I want you to point in space to where the other corners of the cube are. Obviously not the top one, that's vertically above. Where are the other corners of the cube? Off you go. You have to do it to be convinced. Okay, so the modal response, particularly if this is a bad audience because you guys are sort of used to spatial things. If you take a normal audience, they go, well, here, 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 and here. They point out four corners. And they're sort of completely unaware that they've lost some corners somewhere. Because a cube, think of it in this normal, it's got 8 corners. Some of you, I won't call you out, will have pointed out 4 corners. you did something very interesting, which is you pointed out a shape with 4 corners like this, which is basically 2 square-based pyramids stuck base to base, right? That's the shape most people point out. That's the modal shape. Not most people, but a large number of people point out that shape. That shape has a very interesting property, which is that it's the dual of a cube. It's got exactly the same symmetries if you replace corners by faces and faces by corners. You see, it's got 8 faces, whereas a cube only has 6 faces. And these faces come in 4s. So what you know about a cube, which is strange given its name, is that things come in 4s. Now there's a completely different view of a cube, which I'll call a hexahedron. It's such a different view that it needs a different name. And a hexahedron consists of a tripod like this, with right angles in the tripod, and another tripod like this that's rotated 60 degrees. Okay? So I'm showing you where all these fingers join is the top corner and the bottom corner, and there's a benzene ring there, which is the other corners. Okay? They form a zigzag ring of 6 corners. Now, you just don't see that. If you're a crystallographer, you see that. But if you're not a crystallographer, and maybe if you're a brilliant mathematician, you see that, so you have to be careful around here. But most people don't see that at all. And this is just, the square diamond is kind of, people are used to that, and it doesn't really impress them. But this thing, how is it that you just know nothing about where all these pieces are, and it's a cube? And the answer is, I forced you to use a coordinate system where the body diagonal was one of the axes, by saying there's the bottom corner, here's the top corner. I'm forcing you to do it relative to this coordinate system. And relative to that coordinate system, there's a nice simple shape called a hexahedron, which is this guy, but it's utterly different from a cube. The reason I go on and on about this is because the neural nets we have now that do vision do not have these 2 completely different views of a cube. You put in the cube, they're doing stereo, let's say, they're doing 3D vision, they can see where all the edges are, but they don't have internally 2 utterly different representations of the same thing. And that tells us something. It tells us they're not doing it the way people do it. For those of you who like these kinds of puzzles, I'll give you one more puzzle that you can do in your spare time. Take a tetrahedron, that's a triangular base and 3 triangular faces, okay? And now imagine slicing it with a plane so that you get a square cross-section. Most people think, wait a minute, it's all triangles. It turns out, now something more impressive is, if I take a solid tetrahedron and I slice it so I get a square cross-section, and I give you the 2 pieces, and I tell you, these are 2 halves of a tetrahedron, all you have to do is put them together to make a tetrahedron. Okay, I did this on MIT professors, and it turns out the number of minutes it takes you is roughly proportional to the number of years you've had tenure. It's slightly dodgy because someone who had tenure a long time just gave up. And Carl Hewitt, who invented things called actors, after 10 minutes he had a proof that it was impossible. Now, this is a 2-piece jigsaw puzzle, right? What's more, all the faces are different shapes, so you can solve it by just saying which 2 faces have the same shape. They're the ones that have to go together. Because if I put 2 things that don't have the same shape together, I'm going to get a little sort of, there's going to be a piece where it doesn't fit, right? Intrinsically, it doesn't seem like a difficult puzzle. But what happens is your perceptual system sees these pieces and imposes a frame of reference on the pieces, and then you just can't see the answer. Because it does the equivalent of the sort of hexahedron versus cube. It sees the pieces in a way where it's using coordinate frames that don't line up with the coordinate frames used for tetrahedron, and you can't do it, it just blocks you. We have to take this kind of evidence into account if we want to know how people see things. ConvNets can't do that. ConvNets can't fail that way. Okay, my capsules can. Okay, I've given you lots of motivation. You probably want to know how the things work. Well, we can skip all this stuff. So, okay, here's another argument. People doing neural nets will keep telling you it's very important to take this high-dimensional data and find the underlying manifold. Because once you've got the underlying manifold, you can interpolate and you do all sorts of things. They won't often say, once you've got the underlying manifold, you can extrapolate for huge distances. Because after all, the manifold is kind of, the underlying manifold is kind of like this. And you can use a Taylor expansion to get some distance, but you can't go huge distances. But what if the data they were dealing with was well known to have an underlying manifold that's completely linear? What would you think of researchers who spent their time preaching that you should find this underlying manifold, because that'll make life easy, but there was a well-known linear manifold that they weren't finding? That would be silly, right? So what's that linear manifold in vision? Well, we use it all the time. If you want to take two faces and you want to blur between them, you could get yourself a great big neural net. But an easier way is to find the coordinates of identified feature points in the faces, like the centers of the eyes and the tip of the nose and the corners of the mouth. Get those coordinates, figure out how to redraw the face from the coordinates. So do that the other way. And then if you want to interpolate between two faces, you have a texture bit which we'll ignore, but if you want to interpolate the shape, what you just do is interpolate coordinates. And in fact, you can now extrapolate coordinates to make cartoons and things. Because in the coordinate representation, things are linear. There's this wonderful linear manifold, whereas I change coordinates linearly, I get more faces. I don't get things that aren't faces. If I apply the same linear transformation to all the coordinates, right? If I apply one transformation to where the eye is and a different transformation to where the nose is, it messes up the face. But if I take the coordinates of the eyes and the tip of the nose and the mouth, and I apply the same linear transformation to all of them, hey presto, I get another perfect face. It's just a very different size or position or shear or whatever. So there's this very prominent linear manifold that underlies shape. Graphics people know all about it because that's the representation they use. Graphics people use this representation. This is graphics from about 30 years ago, where I read the first 3 pages of a textbook and thought, they do it too. So they take these coordinates and they transform them. They take coordinates of a big thing. From that, they compute coordinates, like coordinates of a house. And from that, you can compute the coordinates of a window and the coordinates of a door and the coordinates of a roof. And they do a whole bunch of that until they get to a whole bunch of triangles. And then they do rendering, which is something quite else. But it's not until they get to there that they start dealing with the properties of light. Before that, it's all geometry. And the way they deal with all this geometry of parts and wholes is by using the coordinate representation. So the idea of capsules is we're going to do the same thing. We're going to try and get those properties of an object. Some properties will be things like the albedo or the velocity or stuff like that. But we want a bunch of properties that represent the coordinates. That is, in the right matrix representation, we want a representation of that captures position and scale and orientation and shear as a bunch of separate numbers. So a long time ago, I was really interested in how you deal with these 60 viewpoints. And I proposed that you have neurons that have great big receptive fields to represent a viewpoint, and then you overlap a whole bunch of them. And it turns out in 6D, if you have big fields overlapping, you can be much more efficient than if you have small fields. If you have a tile of space with small fields, you need a huge number. If you make the fields bigger, if you make the field 10 times as big, you need 10 to the 5 less neurons. It's the dimensionality minus 1, so it doesn't work in 1D. That's called coarse coding, but it's still not efficient enough. And that was because I wanted to be able to represent several things at once. But if you make the commitment that you can only represent one thing at a time, you can get away with just having coordinates to do it, and so you can go back to the graphics representation. And of course, once you got to that representation, you can do massive extrapolation. So if you think about how neural nets deal with viewpoint variation, the way neural nets do it at present is you put viewpoint variation in the training data. And if you ask, is a neural net going to be able to see a small amount of viewpoint variation in the training data and then deal with a massive viewpoint variation? No, it's not. Capsules, if they ever worked, would be able to do that. I'll talk about dynamic routing at the end. Yeah, I talked about that. So here's another example, just in case you're not sick of them yet. If you show people this country and ask what country it is, many people say, not now you've been primed to know that orientation is crucial, many people say, well, it's a bit like Australia, but it's sort of the wrong way round. So Sydney is sort of here, but you know, Perth is over there. But as soon as you realize that the top might be up here, you realize it's Africa, right? Now, you can get away with this in the States calling Africa a country. Here you realize Africa is not actually a country, but naked. I'm going to cut the mental rotation. So I mentioned this already. What I want in these neural nets is not that when you change viewpoint, the representation is invariant. I want the representation to be equivariant. So here's a basic convolutional neural net. You take an image, and you convolve it with a filter, and you get those hits. Now you move the image over, and you convolve it with the same filter, you get those hits. And what you'll notice is that it's not the same hits. It's the same pattern of hits. So what's happened is, that's an equivariant representation. The activation moved when the image moved. And you can imagine the same for all the other degrees of freedom. So that's intrinsically equivariant. So there's nothing about convolution that makes things invariant. It was the max pooling that made things invariant in convolutional nets. And I want to distinguish two types of equivariance that we're going to try and get into capsules. If you move something slightly within the receptive field of a capsule, what will happen is, let's suppose we were coding its position by two activities that represented its x location relative to the center of the receptive field and its y location relative to the center of the receptive field. If you move it slightly, it'll stay represented by the same capsule, so the logistic unit that says that this is present won't change, but the numbers that say where it is will change. I call that rate coding, okay, because the values of the numbers changed, but which numbers were involved didn't change, which neurons were involved didn't change. If I move it a lot, it's going to move to another receptive field, and now the fine position is going to be coded by where it is relative to the center of that other receptive field, but the coarse position is going to be coded by which receptive field it's in, which capsule is active. So we've got two different ways of coding position. We've got place coding, what a neuroscientist is called place coding, which is which capsule is active, tells you what it is, and there's rate coding, which is how active things are, tells you what it is. And of course in the brain, when you're dealing with only one thing, like if you've only got one right eyeball, and you want to sort of specify where it is, you can use rate coding for that, to specify what angle it should be at. And when you've got multiple things, you have to use place coding. So low down in processing the visual image, there's lots of edges, and so we better use a whole bunch of capsules that are small. Each capsule, by being active, we'll say we've got an edge around about here, but it will have several dimensions, and the relative values of those dimensions will tell you where it is within that receptive field. That's what a neuroscientist will call the phase of a conjugate pair of simple cells. Okay. And when it moves a lot, it'll go to just different simple cells. But if you have two simple cells in a capsule, then the fine position will be coded by the phase. And the idea is, what we're going to do with capsules is we're going to try and turn place coding, so the ultimate place coding is pixels, which just have places. Well, they have an RGB rate, a rate for RGB, but that's all. And they have very, very fine places. And what the visual system's going to be doing, the inferotemporal pathway, is turning place coding into rate coding. When you get high up, I don't want a whole bunch of different face capsules. The reason I don't want that is I want to associate properties with the fact that this logistic unit that says there's a face there is active, and I don't want a whole bunch of different ones. What I want is a sort of face capsule that covers a big area that I'm looking at in central vision, and I want the different properties of the face, like exactly where it is and what orientation. I want that in rate coding. So the inferotemporal pathway is a device for turning place coding into rate coding. I said that already. if you can get coordinates, then you should be able to do huge extrapolations. So here's probably the most important picture. This is the basic idea of the talk. Here's a capsule, and let's just concentrate on geometry for now. It's got some active units that represent the coordinates of the mouth. These are the things someone would extract if they wanted to blend faces. For one face, they'd extract these things. And it's got, because it's a capsule and it's doing vision, it's got this logistic unit that's trying to decide whether there's actually a mouth there. We've also got over here, we've got a capsule that detects noses. It's got the coordinates of a nose and something that says whether it exists. Then up there, we've got a capsule that's going to detect a face. So you could just say, you know, a mouth is evidence for a face and a nose is evidence for a face. Let's just add them up and say there's a face. And if you're looking at a Picasso, that might be a good bet. But notice, even in a Picasso will jumble up the relationship between the nose and the mouth. But of course, within the mouth, he still has to keep the relationship between the pieces, because otherwise it wouldn't be a mouth. So you can cheat to a certain extent, but for you to identify any part, you do it by the spatial relations. So okay, sorry about that. So now the idea is, if I find a nose and I know its pose, I'll call that the pose, I can multiply that by a matrix and get a prediction for the pose of the face. Let's suppose faces are rigid things. And if I find a mouth, I can predict the pose of the face. And the way I'm going to see whether this nose and this mouth are correctly related to be segmented together is by getting them each to make a prediction for a face. If they agree, hey presto, there's a face there. Now, ask what happens now if I change viewpoint. So notice what I need up here is an ability to look at this vector coming in, or actually this is a little matrix really. Look at this little matrix coming in. That's a prediction for the relation of the face to the retina. And look at this little matrix that comes in, that's this guy times this guy. And I need to take those two matrices and say, are they roughly the same? That's where I need this thing that looks at covariance, covariance of activities, rather than covariance of an activity with a weight vector. And the thing to notice about this is that if I now change viewpoint, suppose I've learned this. Suppose I now take a radically new viewpoint, which by sheer good luck still left the same pieces visible. So we're not dealing with occlusion yet. I get a very different pose for the nose. I get a very different pose for the mouth. I multiply by the same matrix here, because this matrix represents the relationship between a mouth and a face. And that is something that is genuinely viewpoint invariant. How your mouth is related to your face doesn't depend on viewpoint. That's just an intrinsic property of the face. Of course, in order to be able to represent this intrinsic property by a matrix like this, you have to have a coordinate system for this and a coordinate system for that. And if you choose different coordinate systems, you'll get very different matrices here. That is, you'll get, well, different decompositions, and that's what all this hexahedron versus cube is about. But if you take this matrix, it'll vary as you vary viewpoint. You multiply by this matrix that's fixed, and really does capture the intrinsic spatial structure, completely independent of viewpoint. So that's much better than what pooling does, which says, over a little region, we'll try and make it independent. This says, at least for this capsule, which I agree only works over some small region, we'll get perfect independence here of the knowledge from the viewpoint. And you make a prediction. This varies, but the fact that they're the same doesn't change. Now, you should immediately start worrying about scale, and how similar these are depends a bit on the scale and so on. And so you're going to have to do some normalization to anyway, but you get the basic point. This system, if you can extract these, is a viewpoint invariant way of recognizing the face. Okay, so now the question is simply, can you make that work? Can you design these, this thing that detects agreement so that you can make a visual system like this work. Notice this is much more like good old-fashioned geometric vision. So what happened in vision was back in the sort of 80s, yeah, I talked to David Lowe in about 1981, and this is David Lowe's view of vision from about 1981. It's sort of geometric vision. This is a Hough transform, essentially, a high-dimensional Hough transform. It's a non-parametric Hough transform, because in Hough transforms, what they would do is they would take this space up here and grid it and look for hits in the same cell of the grid. You can't do that in a six-dimensional space. It's not efficient enough. What we need to do is just take a bunch of votes and have some way of seeing if the votes agree. You can't do it by gridding, but it's still the same idea. What happened in vision is David Lowe designed SIFT features, and SIFT features were designed so you could get these guys. But SIFT features also had a whole bunch of descriptors of the SIFT feature. And then machine learning came along, and those dumb people in machine learning threw away this and just kept the 128 descriptors of what's going on in the image patch and said, look, we can do machine learning on this. And then vision turned into doing machine learning on SIFT features or their derivatives, which was just crazy. And eventually people sort of started thinking about, you know, how do we deal with geometry properly? So you could think of me as saying, I want to take vision back about 30 years. When you're old, the only way you can stay current is to drag the field back to 1986. If you can drag the field back to 1986, you're in good shape, because that's when you can still think. So I'm going to try and do this for neural nets one more time. So what we really ought to be doing is saying, what's the real lesson of neural nets? Is the lesson of neural nets that ReLUs are the way to do everything? Well, maybe it is. I mean, ReLUs really are the way to do everything. Not quite, not recurrent nets necessarily. But that's a very interesting lesson. But they're not qualitatively better than tanh and things, they're just better. Is the lesson that a big flat layer of neurons and lots of layers is the way to do everything? Well, it's true it works depressingly well, but it's not very satisfying. If you're a computer scientist, you believe that the way to deal with structure is with modularity. So I have some sympathy for crazy people like Steve Pink who think everything's modular. And this big flat stuff is very unsatisfying. This is much more modular, right? We have these little modules. Is the lesson of neural nets that stochastic gradient descent will really fit models well if you have a lot of data and you train them discriminatively? I think that's the real lesson of neural nets. I don't think, I mean, these architectures that we apply it in, sure, the architectures have been selected so that this stochastic gradient descent on mini-batches on huge data sets with a discriminative objective function works well. But once you've seen that, you ought to believe that if I take any old combination of functions, maybe they need to be smooth, maybe they don't even need to be smooth. They shouldn't be too unsmooth. They shouldn't be gratuitously discontinuous. Take any old combination of nonlinearities, stack it up, and maybe vector nonlinearities, why not? Stack it up, go from pixels to categories, and train it with stochastic gradient descent. And if Ilya were here, he would say, how could it fail? It's going to work, right? And some will work better than others, and why do you believe that ReLUs will work best? So convnets definitely work better than non-convnets. I mean, there's overwhelming evidence now that if you're going to put in any structure, put in replication of feature detectors over position. That's just a no-brainer because you know in advance some knowledge, which is you want your visual system to be able to deal, you want the knowledge in the network to be the same everywhere. So you want the knowledge to be translation invariant. It's not that you want the representation to be translation invariant. When you translate, the representation can change, the rate coding bit of it and the place coding bit of it. But the knowledge should be the same. And that's what you're putting in when you make a convolutional net. You're saying the knowledge should be the same everywhere. And if I learn something here, I want that knowledge to transfer to over there, and I do that with the weight sharing. But once you've seen that there's a huge win from putting in a basic observation about the nature of the task, which is the knowledge should be the same everywhere, why not get other huge wins by putting in a slightly more detailed observation about the nature of vision, which is the thing that causes real problems in vision is viewpoint and segmentation. Those are the two biggest things. And viewpoint causes real problems because it takes the information about a part of an object and moves it to different pixels. If you think about that, that's crazy for machine learning. You have an input vector, and what you're doing is taking some information and moving it to different components of the input vector. That's like if you have a medical record, and one hospital codes things as blood pressure, age, financial status. And another hospital that's more in tune with American medicine codes things as financial status, age, blood pressure. And you try and do learning without unscrambling that. That would be insane. It would actually work in the end, maybe, but you'd be making life very hard for yourself. That's what viewpoints to images, and you have to unscramble it sensibly. This can deal with viewpoint in a more principled way. Convolutional deal with the translational aspect of it, and people have tried extending that to deal with rotation and shear and scale, but then you end up gridding a high-dimensional space and it's hopeless, because convolutional lets you essentially using gridding. The proposal here is we'll deal with that translational aspect, which is the biggest aspect, by gridding again. We'll have capsules, and if you move something over a lot, it'll be a different capsule. This will be another nose capsule that captures noses in a very different position. But within a certain region, we'll deal with it by varying the activities of things that code the position relative to the center of the capsule. So this is going to be convolutional. It's going to have a 2D grid of these capsules to deal with the big translations. But then the other things it's going to deal with in a totally different way. It's going to deal with them by using these matrices and multiplying by matrices that are independent of viewpoint and having devices that can detect agreement of two incoming things. I've almost run out of time, so I will show you something like this sort of working. Okay, just to show you that this was done in 2014 at Google. What we're going to do is we're going to have MNIST digits, because if it won't work on MNIST, it won't work. And we're going to have 10 top-level capsules that are meant to cover the whole image, and lots of other capsules, which are all going to be trained by stochastic gradient percent using a discriminative cost function. And I'm showing you the votes that the top-level capsules get from all these other capsules, and there's a lot of votes. And votes, the strength of a vote is the size of a circle. So the little dots are tiny votes. The circles are big, strong votes. The colors tell you where these votes, something about which other capsules, which type of capsule these votes are coming from. And you show it that, and you look at the votes you get for the top 10 capsules, the 10-digit capsules. I'm just showing you a few of them. There's other ones over here that don't fit on the screen. And what you see is that the big votes cluster tightly for the 5. They cluster a bit for the 1, but there's less of the votes. And if you look at the variance here, the log of the variance, this is tight because that's a negative number. If you look at the 1, it's not such a tight variance, and these other ones aren't such tight variance. The reason you can get big posterior weights on these votes when they're more than a standard deviation away from the mean is because these are votes in a 12-dimensional space, and I'm just showing you the first 2 dimensions. So this guy is actually quite close to the 12-dimensional mean. He's just a bit far away in the first 2 dimensions, but I can't show you in 12D. So this is an example of something that, on a system like this, the basic one got down to about 70 errors on MNIST. A variant on it got down to like 35 errors on MNIST. No, 37 errors on MNIST. So it worked really well. Sarah Sabor has a more recent version of this that got down to 25 errors on MNIST. And 25 errors on MNIST is about as good as any one system does, unless it's done by Jimmy Barr, in which case you might get 22 errors. But you have to add 3 because it was done by Jimmy Barr. Okay, so it can actually be made to work. I didn't tell you all the details of this. Recently, Sarah Sabor, a version of this, she's got it to get the record on basic NORB. So the NORB database has objects that are all the same color and taken from many viewpoints. So it's kind of ideal for this approach. And people don't use the basic version much anymore because it's fairly straightforward. But the record on that was 5%, and she's got down to 4.8%. And we still don't understand exactly what's going on inside this catch-all system. So we're going to be able to make it work much better. So it's 1 o'clock and I'm done. Yeah, I have a meeting at 1:30, so I need to leave at 1:05. Yeah.
Same information, the data sets okay.
That's a great question. Do you need to know the viewpoint on the images? In NORB, you do actually know that information, but that's not used in training. But these parameters, you're seeing the first 2 parameters here, but the other ones, these are the activation parameters of the 5 capsule. They do code viewpoint information. So here's something crazy people do at present, when they're training on shape recognition. They take the images and they transform them so they get a bigger data set, and they train their net to get the right class of the transformed image. So they apply a transformation that they believe will not change what shape it is, like a shift or a rotation. But they don't tell the neural net what the transformation was. And they can't really tell the neural net what the transformation was because they don't have a canonical basic frame of reference. But they could easily give the neural net a pair of images and say what the transformation difference was. And if you gave it pairs of images and told it the transformation difference, you'd be giving it much more information and much more helpful information. So these kinds of nets, the right thing to do is to give them, if you're going to give them transformed data, if you give them transformed data and you tell them the delta, you're giving much more helpful information. Yeah.
I think it makes sense. It makes sense. If you want to learn something, do you think that whole
Yes, I think that's just a property, that's just the nature of vision. Now, it's not quite true because we fixate on interesting places, and so the statistics of fixation-centered images is not uniform. But let's suppose it is, because to first order it is. You want the same knowledge everywhere, and low-level knowledge about edges is the same everywhere. High-level knowledge about faces is the same everywhere. So I want the knowledge at every layer of this net to be the same. But what I want is to get that knowledge into a capsule that works over a big range at a high level and deals with the variation using rate coding by changing the relative activities of neurons, rather than by using place coding by changing which neurons are active. Because once you've got it into rate coding, it's much easier to learn properties of the object. Yeah.
like we thought about the number, like if you the problem, say number of particles, like do you think number of capsules that you need for linearly or exponentially?
I don't really get the point of the question. It's obvious that if you have a bigger image and you have
higher resolution,
you need more capsules to capture the fine detail and so on. But I think that just grows sort of linearly with the number of pixels, which grows quadratically with it. So I think the number of capsules you need should be sort of linear in the number of pixels. But if you wanted to do more things, to have more different types of things it knows about, you need more capsules. So I think it's a good bet that if you want a capsule system that works really well, you're going to need about 1 billion neurons, because that's what we have. Last question.
I think the single capsule layer can be implemented somehow functionally by several layers of the.
That's an extremely good question. Extremely well. If this is the right thing to do, when you train this net full of ReLUs that has multiple layers, it's going to do it. That is, if there's a huge win for doing this kind of thing. And ReLUs, of course, are kind of linear, at least in their working range. So the thing that keeps me up at night is, it's all very well to have this kind of theory, but maybe ReLUs can just fake it. Maybe ReLUs are doing this, but because you compute everything and it still works the same, we just can't see that they're doing that. But I think that's a really good question.